Welcome to the Explainer. Okay, today we are taking a literal trip back to 1998 to look at the blueprint that, quite frankly, built the modern digital world. The mechanics we're about to discuss actually dictate how you found this exact explainer and basically everything else on the internet today. We're dissecting the original research paper by Sergey Brin and Lawrence Page, outlining the anatomy of a large-scale search engine they called Google. Imagine the monumental task of organizing the early, wildly chaotic internet. It was a time when the web was growing exponentially, but our tools to navigate it were completely breaking down. That is exactly the puzzle we're going to break apart today. Okay, let's dive into this. 10 to the power of 100, also known as a Google. Brin and Page actually picked this absolute behemoth of a number for a very specific reason. Why? Because the World Wide Web was expanding at a scale that was completely unorganized and almost incomprehensibly massive. They knew right from day one that they needed a system built specifically for that exact astronomical scale. Part 1, the 1998 Web Search Crisis. To really grasp the genius of their fix, we've got to talk about the sheer chaos of the late 90s internet. Just look at this timeline. In '94, the World Wide Web worm handled maybe 1,500 queries a day. Fast forward just 3 years to November 1997, AltaVista is getting hammered with roughly 20 million queries daily, and the projection for the year 2000 was in the hundreds of millions. This incredibly rapid growth was literally pushing existing hardware and algorithms to their breaking points. Users were just constantly buried under a mountain of irrelevant data. And this brilliantly illustrates the core issue. The old, traditional way relied on vector space models, which is just a fancy way of saying they counted and matched keywords. If a page spammed a word enough times, it ranked first, which meant you got a massive amount of low-quality junk. But Google, they proposed a completely revolutionary approach. They wanted to make heavy use of the hypertextual link structure of the web itself to achieve high precision. They wanted the absolute best documents, not just any document that happened to contain your search term. Section 2. Enter Google, a hypertextual solution. So the big idea here, they realized the internet wasn't just a giant pile of isolated text files. To make sense of it all, they invented PageRank, which is essentially an objective measure of a web page's citation importance. Think of it like academia. If a research paper is cited by a bunch of other respected papers, it's a big deal, right? It's authoritative. Brin and Page just applied that exact same logic to hyperlinks. Every link from one page to another is basically treated as a citation, a vote of confidence from one creator to another. And to demystify the heavy eigenvector math running under the hood here, they used this amazing analogy in the paper. They wrote, we assume there is a random surfer who is given a web page at random and keeps clicking on links, never hitting back, but eventually gets bored. It is such an intuitive way to look at it. The probability that this random surfer eventually lands on your specific page, that becomes your PageRank. If your page is cited everywhere or cited by massive authoritative hubs, you are naturally going to capture that random surfer way more often. Part 3. The power of anchor text. Now here's where it gets really clever. It wasn't just about counting the links. It was about the descriptions embedded inside them. So the crucial point is, before this, search engines usually associated the text of a link only with the page it was written on. Google flipped this entirely. Instead, they associated the text of a link with the page it points to. It sounds simple, but it was an absolute game changer. It let Google accurately index things a text-based crawler couldn't even read yet, like images, programs, or vast databases, simply by trusting what other people were calling them. But man, pulling that off took some serious computational muscle. Check out this scale. In their very first crawl, they downloaded 24 million pages, but they extracted and indexed a staggering 259 million anchors. Processing that much anchor text and propagating all those weights efficiently, that is an immense amount of heavy lifting for a university project in 1998. Section 4. Under the hood. System anatomy. So how do you actually process hundreds of millions of anything on late 90s hardware? Let's move to the architecture and see how this builds step by step. First, the URL server sends lists of URLs to multiple distributed crawlers, which are out there fetching web pages as fast as their connections allow. Then, a store server takes those pages, compresses them, and drops them into a central repository. Finally, the indexer and sorter step in, pulling everything apart to map the words to the documents and build out an inverted index. It's basically a relentless, highly optimized assembly line for data. Part 5. Scaling the future of search. Now, the theoretical math is brilliant, but the physical realities of managing tens of millions of documents, that required some serious engineering magic. Look at this total data footprint. The compressed repository is 53.5 gigabytes, and the full inverted index is 37.2 gigabytes. The entire system, holding 24 million pages, fit into roughly 109 gigabytes. You have to remember, in 1998, a standard disk seek took a painfully slow 10 milliseconds. So Google heavily customized their data structures to avoid those disk seeks whenever possible. They tightly packed their hit lists and optimized absolutely every single byte to make searching blindingly fast. And hardware wasn't the only challenge holding them back. Crawling the web meant fighting massive DNS lookup bottlenecks and juggling asynchronous inputs for hundreds of open connections all at once. Plus, you've got to love the human element here. Running a crawler at 100 pages a second meant interacting with tens of thousands of webmasters. The authors actually noted they had to constantly pause to handle emails from surprised and definitely sometimes angry website owners wondering why a Stanford machine was suddenly vacuuming up large chunks of their website at lightning speed. Section 6. The payoff and the mission. So what did all this brilliant engineering actually achieve? Well, the paper used a very specific real-world query to prove its point: Bill Clinton. At the time, if you typed that into a standard commercial engine, you'd often get a joke of the day site or just pure keyword spam, pages that just repeated the name over and over. Totally irrelevant. But Google, it successfully returned the actual White House website. Through the objective application of PageRank, anchor text, and word proximity, they proved they could bypass the junk and give users the most authoritative results. But their ambition went way beyond just making a better search product. They stated right in the paper that Google's goal was to set up a space lab-like environment where researchers or even students can propose and do interesting experiments on our large-scale web data. Brin and Page were super passionate about pulling search tech out of this commercial, proprietary black art phase. They wanted to offer true, transparent academic value, letting researchers everywhere study the web on a scale that was completely impossible before. And that 1998 blueprint successfully mapped out and organized tens of millions of pages. But it leaves us with such a fascinating question to ponder today. As the internet inevitably scales to billions or even trillions of pages, how will the algorithms that organize our shared reality need to evolve next? The anatomy of Google gave us the foundation, but man, the evolution of how we find information is a journey we are absolutely still on today. Thanks for joining me for this explainer. Keep learning, and I'll see you next time.